This is our last lecture. So remember, after that, there's just one more day, which is the exam. So make sure you review all the lectures. You have all the online lectures, and you will also have some summary or a review session in case you want to review that, okay, or help you with your studies. All right, so today I want to talk about the sum of, and obviously in one lecture can only do a very minimum amount of, can only provide a very minimal description of what we're working on, but some of the interest in the community on how to work with deep neural networks and deep learning, and how we can actually improve over the results and the methods that we have defined to date in this course and in my machine learning class, if you've taken that as well. Now this is, I'm gonna do something really strange here, because you know that I like to have first one lecture where I outline all the mathematical theory that I'm going to use on a second lecture, right, to explain you the types of algorithms that you can develop with that with this mathematics. Because of lack of time, this is our last lecture, and I don't have two more lectures. What I'm going to do, I'm going to first go through some slides and show you what can be done, giving you very minimal account of the mathematical tools that you need to do that. And then after I finish this, I'll go to the board and I'll give you some theoretical concepts as much as we can until the end of the class, okay? And then when we can cover it, great, and when we can't, that's fine, but at least that I want you to understand the very basics of this, okay? Again, this is not a comprehensive review, as I said, for every single topic that we have covered. This is just a selection of topics, mathematical tools that people, including ourselves, are working on to try to understand what does it mean to learn, or in other words, what does it mean to generalize in deep neural networks, right? Generalization means that if I train these machine learning algorithms with a training data set X, and then I test them in a testing data set Z, that my algorithm will work on that testing data set Z. That means, that's what it means, what we mean by generalization, okay? Whereas memorization means that I memorize my training set X, and that's all I know. I have memorized my training set X, but I have no knowledge about my testing set Z. I have nothing to say about Z, right? Now, very important to understand, there's nothing wrong with memorization versus generalization, right? So if you take a math course, say here at Ohio State, in the exam, they're going to test you for generalization, right? They're going to tell you these are the tools, here are some examples, here's some homework, you know, these are the results of the homework, and then in the exam, they'll ask you some different questions, right? Your test set is the exam. And obviously, in the exam, they're going to ask you questions that you've never seen, problems that you've never seen. That's generalization. But if you decide that, you know what, I want to study the history of the United States, and you go and take a course on that, you're going to probably have to do a lot of memorization, right, to pass the exam. And there's nothing wrong with that. It's just a different type of learning, right? Both are learning. They have different purposes, okay? And we just have to understand the difference between them, okay? Now, the other problem, obviously, with generalization that you have to be very cognizant about is that with deep neural networks, as with any other method that I've introduced that uses nonlinear mappings, right, we have no ways of knowing what these methods do. Right? So remember, if I have a function that maps from a domain X to domain Y, right? F of X equals Y, so from a domain capital X to domain capital Y, all right? If I have this function, that function is linear, then F inverse always exists, and I can invert the function to understand what my algorithm, remember, is F, because in computer vision machine learning, most of what we do is F of X equals Y. So if I can invert F, I understand exactly what the algorithm does, right? That's what the inverse means. It tells me what it's doing. Once I add a nonlinear function to it, right, the nonlinear mapping, so if f is nonlinear, then most f's, nonlinear f's, don't have a single inverse, right? There is a problem of one to many mappings when I go from y to x, right? So I do f inverse of y equals x. That's called the pre-image problem, right? And that means that I have no clue what's going to happen for specific outcomes, right? Or what outcomes are going to mean what. And that's the problem that we mentioned earlier that companies have, right? At some point, once you have developed a system and tested with all the testing data that you could collect, that time and money allowed you to collect, then you have exhausted all your resources and you have a system, you have to deploy it to the world, right? Into the wild, and you have no clue what's going to happen. That's huge. Now, so much so that the European Union, when was that, 2-3 years ago, passed a law prohibiting systems that cannot tell you what they do, AI systems, I mean, machine learning, AI, computer vision systems, that cannot tell you how they reach a decision. That basically made deep learning and any other nonlinear method that we have presented here in computer vision and that I discussed in my machine learning course completely unuseful in Europe for commercial purposes, right? Well, this is obviously for serious commercial purposes only, like, medical diagnosis and things of that nature. Now, I don't disagree with that ruling. I mean, obviously, you never know who the gorilla, remember that case that we talked about, who the gorilla in the data set is. So obviously, if you go into the doctor, they do some analysis, and they say, you have cancer, or rather, the AI system tells us that you have cancer, but we have no idea why the AI system says that. Should you believe it? This is a problem, right? When a doctor tells you you have cancer, it's because it said, well, we took some tissue out of your body, we put it under the microscope, and we saw this, and you said this thing here, that means that you have cancer. But if the AI system is incapable of telling you this, then we have a problem, right? So that makes it really hard to know why either the systems that we have described in the last 2-3 lectures that do object recognition, behavioral analysis, face recognition, emotion recognition, or facial action recognition rather, and so on and so forth, why all these algorithms work in some cases and don't work in other cases, right? Makes this extremely difficult. And that's where we are at right now at this moment in 2019, right? We are trying to figure this out. Why does this happen and what can be done? I mean, obviously one solution is abandon this technique and try something else. And maybe eventually that's what's going to happen, as it has happened with many other techniques previously. Most likely this is just going to be one other technique that we have at our disposal, and other techniques will appear, and then we are going to use technique A, B, or C depending on your needs, right? And that's why I try to cover in this course. I hope that the most important thing that you take from, or the two most important things that you take from this course is, number one, a broad knowledge of all the different techniques that are out there to do low-level vision, mid-level vision, and high-level vision, right? This is fundamental to understand. Obviously, if you go somewhere and they tell you which type of computer vision system do you do, remember from our first or second lecture that I mentioned this, never say deep learning, right? Because that is not computer vision. Or don't say PCA. That is not computer vision, right? But if you say, oh, I work in high-level vision, or I work in mid-level vision, whatever you work on, then anyone who works in vision will understand immediately what you do, right? And if you say, well, within high-level vision, I work in face recognition. Within face recognition, I work on the recognition of identity under varying poses, expressions, illumination, what have you, right? they'll understand this. And then you could say, the mathematical tools that I use are machine learning, deep learning, and maybe, I don't know, some other graphical models, right? That's fine. But make sure that you understand the differences between the machine learning statistical tools that we use versus the computer vision problems, okay? All right, any questions before we move on this? So, remember that in object recognition, it's just one of the cases, right? All this applies to every other problem in computer vision, was that, for example, in Imagenet, in 2011, the classification error for top 5 was about 26%. And then AlexNet reduced this tremendously by 10 points, right, in a year. And then that was reduced even more with ZF at 11%. And this was most likely sort of reliable improvements on that particular data set. And remember, this is not the object recognition problem, right? Imagenet is not the object recognition problem. And I emphasize this because many people believe it is. And it is not. It's the Imagenet problem, okay? Which is very closely related to object recognition, but it's not object recognition per se. Now, after that, things got so crazy, you know, with VGG. You know, VGG was one of these first networks that decided, well, what happens if instead of just doing one convolution or two like we were used to, we do a set of convolutions, then we do a set of convolutions on top of a set of convolutions, and then more convolutions on top of that, and yet more convolutions on top of that, and so on and so forth until we get tired of doing convolutions, and then we start doing classification. And that improved even more, and so on, right? GoogleNet, etc. And many people have pointed that this is questionable, whether this is actually improvement or we're just, at this point, really doing something that works really well for Imagenet, for that specific data set, but has nothing of value in object recognition in general, right? And we don't know. That's a point. And then here, that's most likely overfitting at this point once you're getting into the 3.6. And then remember, still, this is top 5, right? This is not top 1. All right. So while this discussion was happening, this paper came out in 2016, which showed that deep neural networks actually can memorize all of the training samples. Right? So let me walk you through these plots because these are extraordinary plots. So this is fitting random labels. By random labels, what they mean is that you take your set X, remember that math cal X that we have, where you have the Xi's and corresponding Yi's, right? That's your training set. What you're going to do is you're going to multiply, if you have that in a matrix form, you're going to multiply this by a permutation matrix. Permutation matrix is an identity matrix for which either the rows or the columns, depending how your data is structured, have been permuted, have been switched, okay? So what's going to happen is that the first image, X1, is now going to be associated after the permutation to label, I don't know, the label of the third image, right? And the second image is going to be associated to the label of the 1,000th image, right? And the fourth image is going to be associated to the label of the first image, and so on. Everything is just going to be randomized. And the point is that some images of tables are going to be labeled chairs. Some other images of some other tables are going to be labeled human. Some other tables are going to be labeled cars, and so on, right? What happens if I train one of these deep neural networks with this totally random or data with random labels? What happens is that the deep neural networks learn to memorize these labels. We know this because this is the average loss, and let's see, yeah, this is the average loss. So this is what it takes to reduce the training error, right? Or the average loss. So if you have the true labels, you see that gradient descent will actually, or backpropagation, will actually force the network to memorize or learn to recognize these images, right? You see that blue curve as the training error goes to 0. Okay? Now, what happens is that when you randomize labels, the data or the images, the training error is still reduced, right? And you can train most deep neural networks to have a 0 training error or close to 0, very close to 0 training error, even if the labels are completely meaningless, right? So how does the deep neural network solve this? Well, it memorizes the image of that table is called car. And the image of that other table is called tree. And the image of that other table is called house. And that's it. So when it sees that table, it says tree. When it sees that other table, it says, what did it say? Car, and this one house, right? Whatever it was. That's it, right? But that's not useful to us, right? It's great that deep neural networks can do that, but it's not what we want them to do. What we want them is to generalize, right? So here in B, this one shows the relative convergence time with different label correction ratios, right? So what you have here is in the x-axis, how much corruption, that means how much corrupted the labels, the yi's, are in your data. And as you see, as this happens, the time that it takes for these algorithms to converge, it means to actually have a training error close to 0, increases, right? So yes, it takes more time, but they all still achieve convergence, right? That's the point. And now this here, C, shows the test error, right? So the test error is, let's see here, shows the test error, also the generalization errors in training error is 0 under different label corruptions. So again, the x-axis has the label corruption, or the corruption of the labels, and here's the test error, right? And you see that as I increase, right? Excuse me, as I increase that corruption, the training error increases, right? And it goes close to 1. It's actually, it goes up to 0.9 because this is on CIFAR 10. I think you might have used CIFAR 10 in one of your projects, right? When we're working with shapes. CIFAR 10 has 10 categories of objects. So classification at chance is 10%. And that's exactly what happens, right? After the corruption is about 80% of the labels have been permuted, then classification is a chance, right? So all I can do is just guess, right? So that's what happens. And the question is, what can we do about this? So here is one proposal that we've been working on and other people have started working on as well. Not the only one, but one of the proposals and one of the things that we can do. So the idea is that, remember, this is a deep neural network with its different processes at each of the layers that we have defined. You feed in the data, and as you do that, since this is a directed acyclic graph, now not all deep networks are directed acyclic graph, but most of them are, right? So since this is a directed acyclic graph, you can define the behavior of that graph, okay? Somehow, we'll see how. You describe the behavior or the functional, or the function rather, of that graph. It's called functional graph. Find this behavioral, and then we're going to use tools from algebraic topology to understand that behavior, okay? All right, so far so good? All right. Now, the type of behavior that, let's think about our, or the behavior that we want to see in these graphs first, okay? Now remember, early computer vision systems used linear models, right? Like PCA, right? Eigenfaces, clear example. Why did we use linear models? Because what we want is to find a general function, f, that maps every x onto its corresponding y, right? And a linear model gives us that. What we do not want is to do simple by simple. meaning f of x1 equals y1. And I could fit in a tiny linear model around x1, right? And if I have a sample that's very close to x1, then I'm going to use this tiny linear model. Now, if I'm close to x2, I'm going to use a different linear model that's around x2, and so on, right? And I can have all these different small linear models around each sample. Why don't we want to do that? Because that's equivalent to memorization, right? I am just saying, well, if that sample that I have now is very similar, say in pixel value or in Gabor values, whatever you're doing, to my x1 sample, then I'm going to do what I did for x1. Why? That's not generalization. It's just it's memorization. That you're applying this memorization, right? So you don't want to have many, many different functions that adapt to every specific sample. Rather, you want a function that defines the general behavior of all your samples, right? That's the goal here. So when you use linear models, that has to be accounted for. And remember that in linear models, we used to add this regularizer in the linear models. That regularizer many times, not always, but many times is used to control that, right? To make sure that you generalize, that you don't adapt too crazy to the training data, so you overfit to that training data. Now, with deep neural networks, this is even worse, because remember from previous lectures, what's a deep neural network? A deep neural network is f1 of x, right? And then f2 of f1 of x, and then f3 of f2 of f1 of x, and so on, right? So you have this composition of different functions, right? All of them, or most of them, nonlinear, that are combined to hopefully find a global nonlinear mapping between x and y. But the problem, the danger now, is that each of these fi's may be adapting very specifically to one or a small number of samples. That's the concern. And that composition does not describe this global general function that we're looking for, but rather learning a specific local transformations, right? That adapt perfectly to the data, but do not generalize to unseen data. So that's what we want to see. So to do that, we're going to use topology, and specifically algebraic topology, which is using algebra methods in topology. Now, to understand topology many times people call it rubber geometry, because it's like you had a rubber, right? Like you when you were a kid, you were playing with these different materials that can be deformed, right? And you can deform the object as much as you want, except for two things. There are just only two things you're not allowed to do. One is you cannot tear your material into pieces, so you cannot cut it or break it, okay? No tears. And you cannot sew or attach two different parts that are teared, okay? So having said that, I want you to see that the coffee mug has the same topology than a donut. And here's the sequence of the transformation that you have to apply to a coffee mug to make it a donut, right? And the fact is that a coffee mug has a hole, just one hole, and the donut has one hole also, right? And that means that I can flatten this part of the coffee cup, right, like this. And when it is flattened, I can make this round and make it look like a donut, right? All these transformations are allowed in topology, okay? Because note, I didn't tear anything or I did not sew anything together, right? Therefore, these two objects, as far as we are concerned, are one and the same, okay? They're identical objects. Now, going back to our lectures in mid-level vision on projective geometry, right? You'll remember that we have Euclidean and similarity transformations, right? We can translate, rotate, and scale things. This is the Euclidean world we like and love, right? Because everything is rigid. In 5460, we already introduced the affine transformation. Affine transformation allows to shear things, right? Because in Euclidean geometry, the basis vectors are orthogonal to one another and of norm 1. But in affine, they don't have to be orthogonal, meaning the angles are not preserved after an affine transformation, and the length or the norm of the basis vectors does not need to be 1, which means that you can stretch things along these basis vectors, right? And that creates these deformations that we are hopefully now very familiar with in affine. In this course, we introduce projective transformations, right? Which go even a step further. So remember, in Euclidean geometry, angles and distances are preserved. In affine geometry, the ratio of distances and angles are preserved. In projective geometry, the ratio of the ratios are preserved, but we don't talk usually about this. One of the few things that are preserved after projective geometry is the concept of straightness, right? If something is straight, right, something goes in one direction, a line, after a projective transformation, it's still a line. That's a major fact about projective geometry, right? I can never bend a line. Well, now we have topological transformations, and the lines no longer have to be lines, right? So now we are allowing nonlinear transformations that the only thing that preserve is what's called connectivity. Okay? So that means if I have a square like this, I have 4 straight lines. I can bend these lines nonlinearly, but you see these 4 points that they have marked these corners? These corners have to still, they are connected, right? So this corner is connected with this corner, means that this point is connected to that point. You see? You see that this corner is not connected to the top one? This corner is not connected to that one either, right? That's the only thing that is guaranteed to be preserved under a topological transformation, okay? All right. You could, in math, this is a classical math diagram. In math, you have what we saw in 5460, inner product spaces, right? I mean, we talk a lot about Hilbert spaces and the like. Normed spaces, right? That's a little bit more generic. We have metric spaces. They don't have to be even defined by any inner product, much more general. And then you have topological spaces, okay? So this is a specific type of topological space, is a specific type of a metric space, is a specific type of a normed space, okay? In the same way that Euclidean is a specific type of affine, and affine is a specific type of projective, there's also this hierarchical structure here, okay? Now, we're going to talk about what's called simplicial complexes. And if we have time after the slides, I'll talk more in detail about this, but let me give you the 5 cents on this, okay? So if you have a graph, remember a graph, it's nodes and edges, that's it, right? So if you have a node, that is called a simplex of 0 dimensions because it doesn't have any dimension, right? It's 0 dimensions. That's just a point, an infinitely small point. So 0 dimensions. If you have 2 nodes connected by an edge, this is a simplex of 1 dimension, okay, or a 1-dimensional simplex. So far, so good? Now, if we have 3 nodes connected with the 3 edges, then we assume the triangle within those 3 nodes and 3 edges is filled. It's actually filled. And that's called a 2-dimensional simplex, also known as a triangle, right? If you have 4 points with all the possible edges, right, which remember it's called a clique, right, then that tetrahedron is assumed to also be filled. And that is a 4-dimensional simplex, right? And so on. You see how this works? I'm sorry, a 3-dimensional simplex, and so on, right? Okay? So far, so good? Now, when you have multiple simplices of these combined together under specific rules that I'll discuss later, time permitting, then you have a simplicial complex. Okay. All right, so far so good. Now, remember, this is a zero-dimensional simplex, one-dimensional, two-dimensional, and three-dimensional, right? That means that this is solid. This is filled within. But if I have, say, 4 or 5 different nodes like this, connected in that way, this is not filled because it doesn't have any simplex of higher than one-dimensional, right? So it has zero-dimensional simplices. It actually has 5 of them. It has 1, 2, 3, 4, 5 lines, means 5 one-dimensional simplices. But it doesn't have any two-dimensional or three-dimensional simplices, right? You see that? Okay. That, on the other hand, is the combination of 2 three-dimensional simplices, right? Okay? All right, so that's what we're going to be looking for. And what we're going to compute is the holes. Remember what I said about topology? Because the points, the connectivity, between all these nodes is always preserved, the number of holes is never going to change after a topological transformation, ever. Holes are preserved after transformation. Okay? So what we're going to do is we're going to define objects by counting the number of holes that that object has. A mug, a coffee mug, has 1 hole. A donut has 1 hole. Hence, these 2 objects are identical. As far as I'm concerned, topologically, they're one and the same. Okay? So that's what we're going to do. Okay. Now, the holes come in a number of dimensions equivalent to the dimensions that we have described for simplices. Okay? These are called Betti numbers. Betti numbers 0, or beta 0 here, is only if it's a Betti number that counts the number of nodes. That's what holes means. Holes of 0 dimensions means how many nodes do I have. That's all it means. Okay? Now, holes of 1 dimensions are going to be holes equivalent to these lines, okay, that we had, and holes of 2 dimensions equivalent to these triangles, right, the 2 simplices that we had, and so on. Okay? So if I have just 1 node, I have Betti number 0, meaning holes of 0 dimensions equal to 1, but I don't have holes of any other dimension, right? If I have 2 nodes, I have 2, 0, 0. You see how this works? If I have 2 nodes connected with a line, I have, there should be 2. I don't know. Oh, this is 1 because I now have just 1 node. Right, I'm sorry. Right, this one here. Okay? If I have 3 with just this 1 edge, then I have 2 and 0, 0. Okay? You see how this works? Now, let's do a more interesting case. Okay? Now, here I have 7 nodes, no edges. That means B0 is 7. The other ones are 0. Once I have connected all of this with edges, I have 1 node, right, 1 object like this, and one one-dimensional hole, right, which is this one in the center, right? I have now all of a sudden this object, and this object has a hole inside, right? Okay. Now, what happens if I add this edge and that edge? Now, all of a sudden, I have, let's see, 1, 2, 3, 4 different holes. You see that? Yeah? Okay. Now, what happens if I add this edge here? When I add this edge, now all of a sudden I have a click here, right, that defines a 2-dimensional simplex. And what did I say about 2-dimensional simplex? It's a filled triangle, right? So I filled that triangle. Now also, I have another 2-dimensional simplex between 5, 0, and 4, right? So I filled that area as well. And now all of a sudden, I have reduced the number of 1-dimensional holes to 3, right? I have, let's count them, 1, 2 that are separated by this line, right? and separated by this line, just this one here, 3. Right? Okay. Let's do one more example. So now I have these 8 different points. So I have 8, 0, 0. I connect them with edges like this. And now how many one-dimensional holes do I have? 6. The 6 sides of that box, right? That is that 3-dimensional box. Now I connect these 2 nodes here with a line, with an edge, and these 2 nodes here with a line. So I create these 2-dimensional simplices and these 2-dimensional simplices. So these are filled. And now I have reduced the number of one-dimensional holes by 2. Therefore, I have 4, right? The other 4 sides of that cube, right? Yeah? So far, so good? Now, if I add this line between 6 and 2 and 5 and 3, then I fill these other sides with 2-dimensional simplices, and I no longer have one-dimensional holes, right? They're gone. But there is a hole inside, which is not one-dimensional, but 2-dimensional, right? It has 2 dimensions, right? So now I have one 2-dimensional hole. You see how this goes? How this works? OK. This is what we're going to compute, right? So what we're going to do is we are going to, the algorithm is very simple. You take your deep neural network, and you compute the correlation of activation. Remember that each node of a deep neural network is activated with the activation function that we select, say a ReLU or a sigmoidal or a 10H, right? You compute that activation at every single node while you're training the network, okay? So at the first pass, at time t equals 1, I train the network, I do backpropagation, and I compute the correlation between every node with every other node, right? And that gives me the correlation matrix, right? Of every node. For rows, it's all the nodes, columns, all the nodes, right? And now I select a threshold for that correlation. Let's say my correlation is rho, okay? My threshold for the correlation rho can be, I don't know, 0.99, 0.98, 0.9, 0.8, 0.7, right? Some threshold. Now, as I reduce that correlation, I consider more node pairs. True? Because if the correlation threshold is 0, then I consider them all, because they're all somewhat correlated or not correlated at all. If I put a correlation of 0.9, I'm going to consider a very small number of nodes, right? Okay? So I'm going to take this as my first variable, that rho value, okay? And now what I want to know is, as I keep adding nodes and the corresponding edges, every time I add a node, or excuse me, a pair of nodes, I add this pair of nodes with the corresponding edge, because that edge indicates that these 2 nodes are correlated, right? I'm going to compute how many holes of 0, 1, and 2 dimensions I have. Okay? And this is what you see here in this plot. So this is here before anything happens, right? So the network has been randomly initialized, right? Random weights, random parameters. So this is the dimensions, and well, this is the number of clicks, which is similar. We'll get, actually, let me go here. Oh, OK, I'll stick here. There are no clicks, right? Which is very related to the holes that I'm going to describe in a second. But as I start increasing the training, there are more clicks, right? So let's see it here. So this is the Betti number 1. Remember, these one-dimensional holes, right? With that rho, well, it's actually called T, not rho. That threshold, right? So when I include very few nodes at 0.9 threshold, there are no holes, right, of one dimension. Why? Because you probably have 2 or 3 or 5 nodes that are just isolated, right? It's just, there are no holes. But as I start decreasing this threshold in this direction, right, the number of holes, one-dimensional holes start increasing, the number of two-dimensional holes start increasing, and the number of three-dimensional holes start increasing as well. Okay? Now, this is at epoch 0. This is before I train the network. That makes sense, right? Because I randomly initialized the network to start creating structures, topological structures that have holes in it. I need to include a lot of nodes of the network with very low correlation between them. But when the network is very well trained, let's look at this last column here, right? Even for much lower thresholds, I have many more holes. What does this mean? Remember, for 1, 2, and 3-dimensional holes to occur, that means that these structures that we have seen here, right, this type of structures have to start appearing, right? And that can only happen in large quantities like this, if all the nodes of the network are interconnected with one another, right? This is the key point now. If these connections, meaning the nodes are correlated with one another, are very closely knit meaning in a small area of the network, right, in the same layer, say in the top region of the second layer, then you're not going to create holes because all the edges of these nodes are going to be connecting the nodes together, and they're going to fill the simplices, right? So you're not going to count nodes. The only way to create holes is by having a lot of long distances edges that connect big structures that don't create cycles or cliques, right? You see that? And that's exactly what we're looking for. Remember from the beginning? We're looking for a function that uses all the different FIs defined by each of these layers of the network to create a global function that works for all the samples. That is what we're looking for. Is the network actually using the whole structure to learn the mapping F, or is it looking a portion of the network, a tiny portion, to memorize the samples? Now, when the network memorizes, what we're going to see is that there are no holes created, right? That this function that you see here of the increase of the number, you see how as we train, there's a huge increase in the number of holes for lower and lower and lower thresholds for every type of holes. If the network is memorizing, this is not going to happen. But if the network is generalizing, this is what we are going to see, right? Okay, any questions this far? All right, good. So with that, not only can you determine whether the network is training or not, you can also use that to train the network, right? So how do you usually train the network? The network, as with any other machine learning algorithm, you will train it using a training set, right? But how do you know when you need to stop training? And the short answer is you look at the training error, right? And you keep training until the training error is small enough, right? We've covered that. The problem with that is that you're just looking at the training error. You don't know what the network is doing, right? But now I just gave you a definition of what the network is doing. And what you can do is you can look at this peak. You see this peak here of the number of holes that this network has. So look at this. The peak is somewhere here, right, at 0.5. Then after a while, it moves here, 0.7, then 0.70 something, maybe close to 0.77, 78. And down here, it's probably at the peak 77, 78. And then you see here, that it has gone back to 70, right? That means that from epoch 50, meaning iteration 40 to iteration 50, there is been a reduction in the number of holes, indicating that the network is starting to memorize. When the network has no longer capacity to find a generalization function, if you force it to keep training, what it's going to do is going to memorize the last few samples that it has. And say, I can generalize these samples, but you know what I can do? I can memorize them. And it will do that. So what you can do, you can actually use that. This is the training error, right? And this is the number, the peak of the number of holes. And you see that the number of holes increases dramatically, or the threshold decreases dramatically of the peak as the training error, training accuracy rather, increases rapidly. And then when it saturates, this stays pretty much flat. And then after a while, it starts moving again. And that's at the point where you say, whoops, my network is already memorizing samples. I should probably stop training because I precisely do not want the network to memorize, right? I want to avoid these embarrassing memorizations that are going to cause me terrible problems once I have finished and deployed the system. All right, I'm going to skip some of this stuff. You have all the details in the papers and in the slides that you have in Canvas, right? So you may want to look into that. But these are just more examples of this, how it works. And here's an example with real data of what happens on a 4-layer deep neural network. So if the threshold is 0.8, right, these are the nodes that are mostly correlated, right, with the correlations indicated by the edges. With the threshold at 0.7, you start creating simplices. With 0.63, you create even more simplices, so you see you have an almost filled structure. And with 0.5, you see that even the insides, right, of this tetrahedron are being filled, right? So, of course, this is just a visualization of all these plots that I was giving you, but in a deep neural network kind of representation. Okay. Here you have another example with another data set, another network. Again, you have all these details in the paper, in Canvas, and the slides, everything in Canvas. The other thing, and this is something that we're still working on, not sure how this thing's going to work out, is that you can take this even one step further and actually use it to determine whether your system, your computer vision system, is going to work in the real world or not, or how well, without any need of any testing data set, right? So let's see how we can do that. Now, this down here is the classical approach I have covered before, right? You have a deep neural network, right? You have a training data, and use this training data to train that deep neural network, right? Once you have finished training, you have some sequestered testing data somewhere that you've never have had access to, and you use that to determine the performance. And then that allows you to compute the performance gap between the test accuracy and the training accuracy, right? And that performance gap tells you how well you're doing, how well you're generalizing to unseen samples, right? Now, I have to emphasize, and I've said this multiple times, this is only an estimate of that generalization gap, right? Because you only have a very limited amount of testing data. What can we do? What we could do is we can now change this based on the algebraic topology tools that I have introduced briefly here, right? So I can take my deep neural network, I can compute my topological space like the one I have introduced before. Then I can extract some what's called topological summaries, which are some properties of that topological space, okay? And then from that, I can infer that generalization gap, okay, on how well this is going to do. So let's see very briefly how you do that. And here is a very quick overview. As I create these structures by varying that threshold that I was mentioning, right? I create these different structures that have more and more edges, right? The number of holes start to increase first because they start appearing, and then decrease as I fill in all the simplices in that simplicial complex, right? You see that? Now, because of this, I can compute some properties of this creation and destruction of holes. And two of them, for example, one is called the life, and the other one is the midlife of these holes. So for example, you see this one-dimensional hole here, what I'm pointing at? Now, this its birth happens here, and its death occurs right here when all the clicks have been included, right? And that distance, right, from the birth to the death, it's called the life of that hole. And the midlife, it's just the average, right? It's the midlife. And you can plot, if you plot these values of life with midlife here, and the generalization gap on the y-axis, you see that this is actual data. There's actually a linear relationship between the creation and destruction of these holes, the life and midlife of the creation of these holes, and the generalization gap. Right? So you can actually regress, you can learn that function, and then once you have a new deep neural network trained on a new training data set, you compute its topological properties, you come here, and it will tell you this functional mapping, it'll tell you what the generalization gap is going to be. That's it, right? It's pretty cool. You don't need to collect any testing data. You don't need to spend time, money, resources. Now, is that the solution? As I said before, the more tools that you have at your disposal, the better, right? So at the end of the day, what are you going to do? You're going to use everything that you have at your disposal. If you have testing data, yes, you're going to use it. But remember, if I have sequestered data, which is ideal, right? Someone somewhere else who's not even related to my institution has some sequestered data. I only have access to that sequestered data maybe once a year. But what I'm not going to do, I'm going to test it this year, and then the results come back to me like I did poorly, and then start modifying things, and then I have to wait for a year until I can test again. Of course, that's absurd, right? So I need some other tools, and these are great tools, right, that I can use to guess how well am I going to perform, right? And that's what all these tools, these different tools, allow us to do. I have included here a summary of the algorithm, some results on how you can evaluate this. I'm going to skip ahead because I'm really running out of time, and I do want to give you some descriptions. I've added here some pictures of the things that I won't have time to write on the board, but you have all these topological properties and diagrams here that you can use for later, okay? And the relationship, so this is very important, how to compute the image. The kernel, remember the kernel is the inverse of the zeros, right, or the empty set, right? So I'm not going to have time to cover all of this on the board, but I just want you to have it here, okay? Any questions before I go to the board? Question?
So can you go back to the linear relationship between the line, this graph? How can you determine there is a clear relationship between the mean life and the delta t?
Because you can test this with a large number of networks and data sets and find that relationship. There is an underlying relationship because of the reasons I have stated, right, between these two different numbers, computable numbers, right? Both the generalization gap and the midlife or life in the topological structure of the deep neural network, both are extracted from the same network. So you shouldn't be completely surprised that there is a relationship between them. But I think that the surprise here is not that there is a relationship between them, but that the relationship is linear, is almost linear. So that as the life of these nodes or the midlife increases, right, or decreases, because it could be a negative correlation, right, the correlation gap increases or decreases as well, right? Okay. All right. Again, details on Canvas. So let me, with the few minutes that we have left, let me go to the board and give you at least the very minimum introduction to algebraic topology that you're going to need to understand these topics, okay? All right, to understand the very basics, let's go back to the definition of the Euclidean space. It always comes back to the Euclidean space, doesn't it? So let's say that we are in the Euclidean space of 3 dimensions. And now remember that that means that I have 3 basis vectors, right? I have my basis vectors I, j, k, or sometimes we have called them E1, E2, and E3, right? So however you want to call them, ijk or E1, E2, E3. And because this is the Euclidean space, the norm of these basis vectors, it's identical to each other, and it's equal to 1, right? And you can write this as E, if you call them EI transpose EI, it's equal to 1. And EI transpose EJ is equal to 0 because they are orthogonal to one another, right? So that's the Euclidean space. Now, in the affine space, right, say the affine of 2 dimensions, remember that I start with, say, 3 points that I'm going to call A0, A1, and A2. And now I select one as my origin, say A0, I select it as my origin. And now I define my first basis vector as the vector from A0 to A1, and my second basis vector from A0 to A2, okay? And that defines my affine space. And so in Euclidean geometry, of course, I had my vectors. So for example, my x vector, if I have a vector here, x, right? This x vector should typically be written as x1, which is the projection on here, x1, right, onto I. So it would be E1 plus x2, E2 plus x3, E3, right? That's my vector, remember? But we typically just write the coefficients, x1, x2, x3, and this is just the standard notation that we've been using since the very first lecture in 5460, right? So during 2 different courses, or the 2 courses on computer vision, we have been using that notation. And here we use the barycentric coordinates, right, that we define like this as well, to define or to write the coefficients. So we can write A0 plus the sum of each xi of I minus A0, right? Where this is my EI basis vector, right? True? And those we call the barycentric coordinates, remember? Okay. So this set, the set of A0 through AP, P the number of points that are going to define my p-dimensional affine space, are said to be geometrically independent. Okay, so the set is the elements, I should say, rather, of that set are geometrically independent if for any real scalar xi, 2 properties hold the sum over all I from 0 to p of xi is equal to 0, and the sum over all I of xi ai it's equal to 0. Okay? Here. If and only if, so I'm going to copy this here because I don't have any more space. If and only if, you see, x0 it's equal to x1, it's equal to xp, which is equal to 0. There we go. Okay. So I'm going to say that my a0 through ap are independent, right? Geometrically independent. If for this to be 0 and this to be 0, the only option is that all the coefficients are 0, right? In that case, they're independent. That's what defines the affine space, right, as we know it. So, for example, a single point AI, right? If I only have A0, that single point is geometrically independent, obviously, right? 2 points, A0 and A1, doesn't matter which ones, they're also geometrically independent by definition. 3 points can be geometrically independent if and only if what? Only one thing has to happen. They are not collinear, right? If they are not collinear, then they're geometrically independent, right? Because they span two-dimensional space. They've defined affine space. And so on, right? So 4 points, they cannot be coplanar. You get the idea. It also applies, or it also follows, that if I write A1 minus A0, A2 minus A0, right, all the way to AP minus A0, these are the different basis vectors that I create to define my affine space. A0 through AP are geometrically independent if and only if these vectors are linearly independent, right? That's saying the exact same thing. You see that? Okay. So with that, let's provide a very useful definition. Let A0 through AP be a set of geometrically independent, so B or a geometrically independent set in RP, then a simplex, let me call it a P simplex, sigma span by A0 through AP is the set of points X in RP such that X equals to the sum over all I from 0 to P of Ti AI subject to the sum of all the Ti's equals 1. Okay. So that's my definition of a P simplex. So let's see some examples of that. So for example, if I have a point A0, this is a 0 simplex because this is 0 simplex because I can have X equal to T0 A0 and T0 would be equal to 1, right? Yeah, that's it. So easy enough, right? So I only have Ti from I0 to 0, right? And they have to sum up to 1. That happens, and this also holds. So that's a 0 simplex. If I have A0 and and A1 here, then this is A1 simplex, because I can write x is equal to t A0 plus 1 minus t A1, right? Can you do that? And then by definition, this t0, if you want, is t, and t1 is 1 minus t. Then they sum up to 1, and their sum is the x's, right? Okay. Let's do one more. If I have 3 points connected with 3 edges, so A0, 1, 2, corresponding edges here, and because this is a simplex, this is a filled triangle, right? So this is solid. Then this is a 2 simplex with, let's see, I can write x is equal to t0 A0 plus 1 minus t0 times t1 over 1 minus t0 A1 plus t2 over 1 minus t0 A2. Okay? This is just one parameterization of the 2 simplex, but that gives you 3 components, t0, t1, t3, that have to sum up to 1. And every x, meaning every x means every element inside that triangle and in the boundary of that triangle, right? Any element is given by that equation, right? Now, also note that for any p simplex, there is a unique geometrically independent set, A0 through AP, right? Spanning it. Okay? Unique. Also, the elements A0 through AP are called the vertices or the nodes of the simplex. P is called the dimension of the simplex. And you will see people use the notation in these closed brackets, A0 through AP, instead of the set brackets here, to indicate that they define the span of the simplex. Okay. Okay. A few more definitions, and I'll let you go. The rest, it's going to be for some other time, right? Next year. So a face of a simplex, right? So let's say of sigma is also a simplex span by any subset of A0 through AP, right? Meaning that if I take any subset of my set that spans my simplex sigma, that defines another simplex, which by definition is a face of the original simplex, right? So, for example, let's see, if I have this tetrahedron here, this one, which is of course filled because I have all the all the cliques in this graph, right? So it's filled in all their faces inside. All the faces are filled, even the interior, right? This is given by, say, A0, A1, A2, and A3, right? These nodes. Now, if I take a subset of nodes, let me take A0, A2, and A3. You see, this A0, A2, and A3 define that face that is also simplex, right? But if I take a subset of this, right, it could be, say, I don't know, A0 and A2. That is also simplex. And if I take another subset, A0, that is also simplex, right? So every time I take a subset of the elements, the nodes, right, the elements that define a simplex, I get a face of the original simplex that is, by definition, also a simplex itself. Now, if you have A0 through AP, and you take, say, AI out, so you have now A0 through AI minus 1, AI plus 1 through AP, that is called the face opposite to A1. Excuse me, AI, right? Okay. All right, so if you take the union of what's called all proper faces, all proper faces are all the faces of the simplex except the simplex itself. Okay? So I can take all the possible faces, and then I take the union of all of them, and that is called the boundary, or BD, of the simplex. That is what is the edge, right, the boundary of my simplex. And I could define the interior of the simplex, as the simplex itself minus the boundary, right? Easy enough. Isn't that cool? It's just very simple math. Just can compute the boundaries. We can compute the interior. Very simple computations, because I just need to take all the possible subsets of that original set. That's all I need. Now, you can, as a homework, prove that remark or result at home to test your skills, your math skills with this. X in the boundary of a simplex has at least a TI equal to 0 and an X in the interior of your simplex. Oh, hold on. Oh, I'm sorry. My bad. All right. So you can prove that if X is in the boundary, it has at least one TI that is equal to 0. That is the TI associated to the AI that you've left out to get that face, right? You see this? And X in the interior, if X is an element or a point in the interior, then all TIs must be larger than 0, right? That's easy to prove. I suggest that you try, because this is really cool. There is maybe another remark that's good to test. There is a homeomorphism between a simplex. So there is a homeomorphism between a simplex and the ball of p dimensions. Well, remember, P, the ball of P dimensions, means that it's a solid ball, right? It's not the sphere of P minus 1 dimensions. The sphere of P minus 1 dimension, remember the sphere of P minus 1 dimensions? It's just the surface of the ball. That is homeomorphic to the boundary, the boundary of the simplex, right? So if you compute the boundary, that is homeomorphic, right? This is homeomorphic to SP minus 1, right? Isn't that cool? Okay, last definition then, and we'll leave it here, but at least you have the very, very minimum notation that you need to read the papers or some of the papers. You'll need to supplement us, obviously, but at least you have some basic knowledge. A simplicial complex let's call it capital K, and RP is a collection of simplices in RP that satisfy the following conditions. Number one, every phase of every simplex in K is in K. And number two, the intersection of any two simplices of K is a phase of each other. What this last one means is that if this is a simplex, right, and this is another simplex, then this is a simplicial complex, right? But I can never have something like this. That is not a simplicial complex. This is not a simplicial complex because this phase is not a phase of the other simplex. You see that? But this phase here is a phase of that other simplicial complex, right? All right, I'll leave it here. So these are just some of the tools that we're starting to work on. The latest tools that I introduced in the last several lectures, right? Combining many of the tools that we had defined before to create these deep neural networks. Now using the topology and algebraic topology tools, mathematical tools to define what these neural networks do, right? And there's still just so much more to do in the years to come. So you have to stay tuned. If you want to work in this area, you cannot just observe, which I know it's a lot, all that we have covered in 5460, right? Introduction to image processing and computer vision, plus what we've covered in advanced computer vision now. But you have to observe all this, plus all the reading materials that I've given you. And then in the years to come, whatever thing new comes out, right? Because this area is advancing rapidly. As I mentioned before, CVPR, which is our main conference, received like, I don't know, 6,000 or 7,000 submissions. I think it was 6,000 or something like that. So you can just get an idea. We're expecting maybe 10,000 attendees, maybe more. This is the interest that there is in the area. I want you to take advantage of this. I hope that these two courses have been useful to you toward that goal. But I want to emphasize this is only the beginning, right? Practice, practice, practice. There's nothing else like practice. Read a lot. You have now the knowledge to read the materials that are out there and understand what these materials talk about, right? So when these materials Because what I'm not going to do here in this course ever is to tell you this is how this specific deep neural network is designed, right? Because that's useless. You can read that now and understand it, right? Because that deep neural network, 2 years from now, no one's going to know what it is because they're going to be using something else, right? But if you understand what precursus analysis is and what least squares and nonlinear least squares and gradient descent and all these different tools are, then you can just go out there, read the books, read the articles, and understand what people are working on or doing or what have they done and how can you apply to your problems. That's what I really hope you got from these 2 courses, okay? That it gave you the tools to actually go out there and do that. With that said, this is a bittersweet moment for me because this is going to be my last teaching for quite a while because I'm taking a long sabbatical and then I don't have to do any teaching for who knows how long. So it's been great teaching these courses and I hope it's been useful to all of you. You have them now on YouTube so you can keep watching them as much as you need, but don't watch it too much. Also read the materials, right? Because otherwise it gets to a point that just listening to me talking doesn't help, right? You actually have to get dirty, put your hands into it and not only read and absorb that material, but then implement in MATLAB, Python, whatever language you want to use, but really, really work on those things because there is an extraordinary need for people like you out there. All right, thanks and good luck.